All right. So you can um yes.
Okay. Does it hear me? Okay, it does. Do we have control over this light? No, we don't. Okay. So our project was to make a robot that could go in a farm through like the furrows in between plants and pick fruit, identify and like cut weeds, something like that, and spread fertilizer. So to do this, we needed a robot that could actually know where it is outdoors, be able to figure out where to go when localization doesn't work very well, and have like an arm or some sort of mechanism to be able to actually pick fruit or cut weeds and stuff like that. So Sean here can show the design. I don't control this, so it's not gonna go to the next slide.
Okay, yeah. So, in order to achieve our tasks, we decided to design a differential. Oh, wait, can we slide? Do we not have control over the?
Oh, this is on there, and
I see.
I'm not sure how old it is too.
Ah, I see. Okay. So, in order to achieve our movement, we decided to design a differential rocker bogie drivetrain. This kind of drivetrain consists of like three main parts. You have the rocker assembly, which is the front wheel, the bogie assembly, which is the back set of wheels, and then you have a differential module in the middle. Basically, the way it works is that each side of the drivetrain can actuate. Each leg can actuate independently. But when one side raises, the other side lowers, keeping the body of the robot always level to the ground. We decided to design this kind of drivetrain because of its the aforementioned stability. But it can also oftentimes be difficult to execute because of its complexity, which is why we're not quite done with it yet. Um, in order to actually achieve the picking and the cutting, we decided to design a triple jointed arm with a differential wrist. Um, this assembly is four main parts. You have the base of the arm, which houses the motors, the actual joint body, which is the thing that pivots around. You have the differential wrist, which can move on both the horizontal and vertical axes. And then you have the grabber claw, which is has an integrated cutter, so you can both grab and cut the fruit at the same time. And we landed on this design because it can do a lot. It can pivot in a lot of different directions. Eventually, it's going to be on a turret, so it can spin around. But as of now, it's just static. Um, Next slide. Yeah, and in addition to this, we have our electrical diagram. Basically, we have a lot of custom circuits on our robot. Some of the main components we have are the battery, the power distribution, the Arduino Mega, and a Jetson. The two main types of actuators we're using are Kraken X60s and Swift servos. And in order to power these, we have a CAN FD board on the Arduino, so we can actually communicate over CAN, which is what the Krakens use.
All right, so we wanted a robot that would be able to work like a overall system that a user would be able to use without needing to actually connect the keyboard, a mouse, and all that stuff to the Jetson. So we made it have it so that when the Jetson turns on, it turns on a Wi-Fi hotspot and does some startup commands to create a server via a program called Unicorn. It uses Fast API, which is like it's a Python library that allows it's basically a framework for using API. And then WebSockets is the actual API we use to communicate with the robot, like the Jets Nano and the interface. That's what we call it. Basically, the website that will be hosted that's hosted on the IP address that the Jets Nano hotspot has. That way, the user can just connect to that IP and then control the robot wirelessly via Wi-Fi. So, you can see that on the screen here. Basically, think about it this way: the server, which is the Jets Nano, sends like telemetry data, and the client, which is the user on their phone or on the computer or whatever, can send commands to the Jetson through this network here. For the front end, we use React to basically make the whole front end work. Actually, like um, and yeah, you can go to the next slide. So here's what the interface looks like. We have some basic commands like off, on, and then like you can set the state of the robot to like resting, gamepad mode, stuff like that. You can also like the user can also control certain variables. Like I have target yaw, turn P, drive PA. All these variables are basically I have them set up there for tuning. It's more for me, but it's like it allows for real-time tuning without having to actually change the code on the robot. It saved me a lot of time. So you can change these variables and then it will send that data to the robot and the robot will actually change those variables in the code. There's a joystick there so the user can just control the robot wirelessly. And then there's a compass show the direction what the robot's facing and a map where the robot where the user can basically see where the robot is and like click on where it wants the robot to go, like where the target position is. And then finally the telemetry data, which basically shows the user basically everything that the robot all the statuses of the robot, like whether or not the Arduino is connected, what the position is, what the target position is, whatever the all of the subsystems, all that information is extremely useful for me because when I'm tuning it, I want to see to make sure these variables or like this information is correct. I do want to eventually add the ability to change the size of the map, to save points to a file, and to load points from said file. That way you can always do the same path over and over again. I can go to the next slide. So here's a system set exists basically for wireless communication. So there's Wi-Fi, radio, hotspot, and then there's of course Bluetooth, and I also include wired. These are all the systems that can be used to communicate with the robot, like have the user be able to control. So um one down. So we chose to use a Wi-Fi hotspot because it can work anywhere. Like you just need to be nearby a robot. You can be in the middle of nowhere with no Wi-Fi access at all. But since the robot is emitting a hotspot, you can connect to that. It does have its cons, like it doesn't have internet connection. It has there's a little bit of signal delay because it's over Wi-Fi and it's limited range. But I figured that's okay because the benefits of accessibility, like you can use your phone to connect to the robot. You don't need a radio controller. You don't need a Wi-Fi network or anything like that. And then with the reason that why not Bluetooth or wired is just because it has a fairly limited range, and plus, it can be kind of a hassle to actually get set up to work. I will say this does have you can use pre-existing Wi-Fi for this. Like I use um pre-existing Wi-Fi whenever I want to do quick changes because it's convenient. But for eventually when you're actually on a farm, it does not need Wi-Fi at all. It just needs to have the robot you make a Wi-Fi hotspot. Yes.
Job so far, Sean. Um, is that a 2.4 gigahertz Wi-Fi hotspot?
I think so. I'm not sure. It's whatever the Jetson already has. The Jetson can already have like make a Wi-Fi hotspot. So
I think the Jetson's 2.4, yeah.
okay, no.
Usually, I mean, many network adapters can produce 2.4 and also 5.
Mhm.
Verify that once. Because these kind of devices within a short range, 2.4 gigahertz, uh, it's easy to broadcast and make it independent. But so if it is 2.4 gigahertz, it will have longer reach for the signal, but the downloads and uploads speeds are less.
Yes. So we figured that in an ideal world, basically that the user only has to tell it to go to the preset path. So it doesn't need like really reactive controls. It's not like a drone where you need it to have like the littlest signal delay. So
Right.
all right, the next slide. All right, so here's our communication to the Arduino. So there's some pre-existing systems like ROS. I didn't use that because I didn't know about it. So I ended up making the system basically where the Jetson Nano will send a command to the Arduino via the serial port. The command just contains what device is talking about and what value it wants to do with that device. So for example, if you have a motor like right drive here, the device there is the right drive. It's ID'd as 2, and then the value is what it does. So like if I give it like the number 100, it'll set the power to 100. Um, but the reason why we have this system in the first place is so because we want the Arduino to be kind of like the intermediate controller when the Jetson Nano can't. So the Jetson Nano runs at 10 to 30 hertz with its Python code, which isn't enough to run, say, like odometry or like really high speed motor controls. So that's what we have the Arduino for. Furthermore, we noticed that if the Jetson Nano were to like suddenly crash or something, the Arduino would just keep doing its previous task. So to overcome that, we have a heartbeat system where if the Arduino hasn't received a signal for say over 2 seconds or so, it basically stops all the motors and just waits for the next command. And then we have our Jetson Nano just sometimes send a ping to the Arduino to remind it that it's still active. And then we have an LED to basically display the status. Like if it's blinking, it's receiving power, but it's not received a command yet. And if it's solid, that just means it's receiving power and it's active. In the next slide. So Mr. Andrew there, he actually taught me about this system, right? The overall structure for the robot autonomous logic. So we need localization and perception for mapping. With mapping, we can create a path. And with pathing, we can decide how to control the robot. Yeah. So for localization, we have these three sensors. So we have wheel encoders. These run extremely fast at 16 megahertz on the Arduino. It's a local sensor and it measures position and yaw. But it does drift over time. Wheel slip, things like that can cause the accuracy to decrease over time. What I've noticed is the accuracy of this actually decreases proportional to movement. Then there's the IMU. This one's a little bit slower than the wheel encoders because it is connected to the Jetson because I'm using the IMU in a camera. It's also a local sensor. I use it for yaw. I don't use it for position because it drifts extremely fast. The drift is actually due to random walk, and it's very accurate. But the accuracy does decrease proportional to the amount of time that passed. So we need a global sensor to kind of keep things localized. So we use RTK GPS. This runs a lot slower at 1 to 10 hertz. It's a global sensor and it measures everything. It measures position, speed over ground, and course over ground. I call it Ornstein. I found the noise type here as Ornstein-Uhlenbeck, which is basically it drifts over time, but it rubber bands back to the average. So if you look at the grand scheme of the GPS noise, it will tell you the average. And the accuracy, it's not super accurate, but it does depend on the environment, and it's still going to be better than not having it at all. All right, next slide. So for our localization, a dead reckoning, when we're not having GPS signal, we rely on the odometry and the IMU. So on the top right here, you can see the code for the odometry. Basically, since it's for that, we're using that robot as a test right now. So it uses something called tank drive. So we use the logic for tank drive to figure out like where the robot is. Then using the IMU, we can read its gyro, which tells us rotational velocity, and with that, we can integrate that for its yaw estimate. So the problem is, if you look at that diagram with the IMU yaw, this is just doing exactly what I said, where it integrates rotational velocity. Notice it's not moving. I have it not actually moving at all, but it does drift over time. So over the course of 2 minutes, it drifted by 0.8 rads, or radians. So that's why to combine the best of both worlds here, I use a Kalman filter to actually combine both of the sensors. And that's the algorithm I use in the bottom left.
Ask a question.
Yes.
You're using two IMUs.
I'm using odometry and IMU. So I only have one IMU though.
It's from the camera.
Yes.
Okay. So the odometry also came from the camera.
The odometry is from the wheels, the wheel encoders. Yeah.
One question. So you're talking about yaw. Where would you need the yaw actually? I mean, is it going come down or?
So yeah, I want to measure like where like the heading of the robot is. So that's important if I want to move to a position because that drivetrain requires you to actually look at where you're driving. Um,
So if your x-axis is your position, or you are using yaw for the x-axis, like for the.
we use a three-axis system basically. So we have X and Y. Like if you imagine a top-down view, like that's X and Y, and then yaw is just its angle basically. So we can go to the next slide. So for global localization, we use GPS. So we have that little chip at the bottom. That's the GPS chip that we use, and that antenna above it is basically it's a GNSS antenna. So we don't just use GPS. GNSS actually has a bunch of different satellite systems. The first four, GPS, Galileo, Beidou, and GLONASS, are like the ones that we primarily use. The other two can be used in their local environments. Like if you're over India or Japan, these would work, but they're not over the United States. So the drift that yeah, uh, GPS does have some drift, but it always eventually rubber bands over the average position. So which means it doesn't actually it is more accurate than IMU and odometry in the grand scheme. Um, but I will say that it is extremely noisy. So this is a sample I took over 5 minutes at the bottom right. The green is longitude, the red is latitude. These are in inches, and 00 is just where this first measurement was. So you can see that it does drift away from that first measurement before it eventually finds its position. And this is with standard GPS. So next slide. So to improve localization, we use something called RTK GPS. So traditional GPS takes information from the nearest four satellites and does trigonometry to find out where it is. But there's some a built-in error to this. So to actually deal with the errors, you need a base station that doesn't move, takes this information from the same four satellites, and then after a while, it actually knows where it is. After a period of maybe like 30 minutes of surveying, it can figure out exactly where it is in the world. And based off of the most recent GPS signals, it can figure out the error in those. It uses radio to send that error information to the robot, which the robot can then use to basically take out that error from its GPS signal. So using that system, I measured longitude here, and notice that the noise here is a lot less. Like here, it's about 10 inches over 5 minutes, which is a lot more accurate than the 100 inches that standard GPS had. And this is actually with fairly low quality RTK GPS because I only had it survey for 5 minutes. The longer the GPS surveys for, the more accurate the RTK GPS will be. All right, next slide. So in order to decipher GPS readings, I have a GPS reading here. So GNGGA is basically the message identifier. GN it means it's GNSS signal. If it was GPS, it would be GP, and the next three letters are what kind of stream we're talking about. So this is a position stream. So it tells us latitude and longitude. But there's not just position stream. GPS can also tell us speed and like orientation. So that would be the GNVTG signal, which tells us course over ground in degrees. So what angle our robot is facing based off of where it's moving. And then speed over ground, how fast it's moving in kilometers per hour. So standard GPS is what I showed you initially. Has about a noise of 1 to 5 meters. And then autonomous is the standard GPS equivalent for GNVTG, the other stream, and it has a noise of 1 to 3 degrees for coast over ground and 0.1 to 0.5 meters of noise for speed over ground. It is important to note that speed over ground is not very accurate if you're not moving. If you're not moving, it still will measure movement just as noise. And then course over ground is it's accurate if you're always moving in the direction that you're facing. But if you're not, it just moves. It just measures the position that you're moving towards, like the angle you're moving towards. So if you're moving sideways, it'll measure your course over ground as that angle, which is not necessarily where your robot is facing. And then you can see here the noise decreases when you get better signal like RTK fixed or differential. All right, next slide.
One question.
Yes.
So in the graph, I see that your speed is varying kilometers per hour.
Yes.
What are you trying to convey in the graph?
So I should label this, you're right, but basically this is no movement at all, but it's still measuring speed. So I'm just showing that there is a certain level of like noise with the speed. The x-axis is it's time. Yeah, in seconds.
Yeah, but even our cell phones, when we're using navigation, when you stop at a traffic light, the GPS doesn't know which direction you're going to go. It keeps bouncing.
Yeah.
And our cell phones also use very cheap GPS. Yeah, their GPS is not that great. Certainly chooses RTK because the RTK correction can happen both from the satellite signal and also the cell phone signals. Very good.
Yeah, so if you notice, we can, but with this information, we eventually will have it so that we can combine our dead reckoning localization and this global localization to make an improved estimate of where our robot is. All right, next slide. So for obstacle avoidance, we want it so that we can avoid obstacles even if localization isn't working. And honestly, even if localization is working, we still need to have an obstacle avoidance system just because the situation may change. So that graph basically shows the logic here, where you need perception, pathing, and control for obstacle avoidance. All right, next slide. So for perception, we have our depth camera. So the reason why we want to use a camera is because it doesn't just see like a scan in front of you; it sees a whole like a lot of information in front of you, like a whole in every axis here. So but I've noticed that the stream data isn't always super accurate. Notice in that raw depth camera footage on the top left, the dark blue represents like points that are really close, but that's not true because those are actually edges. So we have it so that we basically want to filter out bad data. So any data that says it's really close or really far is essentially untrustworthy. And then we also have data that if it's changing extremely rapidly, um like for example, in the bottom left, there's some points that say it's at certain points, like certain ranges, like those dark red and that orange. But that's not correct because I'm actually just have my hand in front of the camera, but it's measuring the distance incorrectly. So basically, we use some logic that basically filters out bad data based off of distance and how much the position changed in one frame. So if a position changes in one frame, like say like if it changed it like 20 inches or something, it must not be right because that's not possible for a stationary object. We also crop out the edges because the edges measure noise incorrectly. Likely because the stereoscopic camera requires binocular vision, meaning it has to have we can only look like inside a certain view. Yes, so the top right is basically filtering out bad data. So the yellow is basic thresholding, where we look at if it's within this distance, it cannot measure accurately, or if it's too far outside this distance, it cannot measure accurately. And then the red points are points that are very noisy, and I don't want to use those for data collection. And then the next image is just overlaying that on top of the original depth stream to basically cancel out bad data. But all the rest of the points there that aren't in red can be used for your mapping and all that. All right, so the next thing we noticed that based off the position of our camera, we actually weren't able to measure obstacles like on like low to the ground. So we added a LiDAR. I just taped it on there. And this was really good. It's much more accurate than the camera. It's much less noisy. But it has a big problem of this is a 2D LiDAR. It cannot measure vertically. So, but combining this with the camera basically gives it a larger view of the world. It also has a much greater range. So by combining the two, we can make an improved map. And in that bottom left, you can see a map we made with the LiDAR, where the red is obstacles, and that big block in the middle is where our robot is. Next slide. All right, so perception for mapping, we just take all these points that we detected, and based off of the position of our robot, we can actually plot these points on a map. So here's the on the left here, it shows a diagram of like the logic. So the depth camera and the LiDAR make an obstacle map. And then when you add in like the rotation, like the orientation of the robot and the position of the robot, you can make a global map of where everything is. As you see on the right, that this is like a vector diagram, but basically that blue is our robot, the yellow is our target, that dark red are obstacles, and then that purple line is where it's going to drive. The red line is where it's trying to the obstacle vector, so we're trying to avoid obstacles, and the green line is the goal vector where it tries to drive to the goal. This is a very simple pathing system, though.
One quick question.
Yes.
Where did you use what's that? I forgot the name of the editor. Uh, how did you get that graph?
So this is I actually made that graph. This is on the interface that I made. So this is just it's very simple. It's just basic JavaScript. So yeah, this is JavaScript. This is on the website that I made, so you can see the map. It's just a basic box with points on it. So Very simple.
What we use for LiDAR thing?
We use some algorithms for LiDAR mapping, right?
Yeah. The one that you use for AI intrinsic challenge?
But we
All the graphics, for graphics, especially using the LiDAR occupancy grid and all, that's part of ROS. What is it?
Arvis.
Arvis.
Yeah, Arvis.
Arvis. Is there a second one?
There's so RQC graph, it's kind of like part of Arvis.
Yeah, within ROS we use Arvis.
Hmm.
It's very popular. It's an industry standard. It's an industry everyone uses that.
I think I showed him yesterday.
Yeah.
So
Yeah, really.
All right, so for pathing, these are the different algorithms we looked at. So artificial potential field is the one I just showed you before. That's the one I've been trying to use, but it does have its cons. So the way it works is basically it thinks of the goal as an attractive force and all obstacles as repulsive forces, and then it averages those two vectors to make where it's going to drive, like the new drive vector. The problem is it can get stuck at local minima, so that would be like a U-shaped obstacle or a sharp corner, something like that, where it cannot navigate around it. This one Andrew's taught me about, which is the dynamic windows approach. I really this is a lot better. It can still get stuck at local minima, but those local minima would have to be much larger. So that would be like instead of a small corner, that would have to be like a big cul-de-sac or something way beyond its measurable range. So the way the dynamic window approach works is it tries to go to its target path, but if it's obstructed, it looks at the path with the most clearance and the path that has the shortest angle and optimizes the path that between those two variables. So greater clearance is basically think of it as if you have more clearance, you have a greater weight, like a greater score. And if you have a greater angle from your target angle, that's actually a penalty, less score. Based off of that, it'll find the optimal path. So that would usually be the one with more clearance but less angle to that less angle difference from where it should be going. And then finally, there's A star, which is a global pathing algorithm. Um, this is really good. It will always find the correct route to go, so it can never get stuck. But it's too slow for obstacle avoidance, especially if you don't know where the obstacles are initially. That's why I like these local paths, where if it sees the obstacle, it can immediately react. It doesn't need to make a whole entire new path or anything. So it's a lot computationally cheaper than A star.
So within the ACE, when you mean it requires nodes, could you explain that?
Okay, so these other algorithms can basically can calculate where they need to go based off of a bunch of points, like where the obstacles are. But A star requires sort of like an actual full map of everything. So what nodes are basically it's basically points that it can travel to, and then certain nodes are like obstructed or have a higher cost. So an easy node map would be like a grid where each point in the grid is a node. But like I said, this is computation expensive because it has to go. The algorithm works by going from one node to the next node to the next node, and depending on how far away your target is, that can quickly compound into a much more expensive path.
Makes sense.
Next path. So this is the how artificial potential field works. It's what I talked about before with the uh, attractive and repulsive vector. And then in the bottom here, it actually shows you a problem. When the obstacle is in a U shape or like a tight corner, it will have a repulsive vector that's the same as the attractive vector, which means it cancels out and just doesn't move. So that's a big con with this. But this is very popular with drones because if there's obstacles in the air, this just pushes it away from it and quickly realigns to the goal. So this is what I initially used, and I have some videos of that. Next slide. So to test it, I've actually made a simulation. You can play it, maybe. Oh, okay. Well, basically, this is a simulation where I had you can click on the map and it will bring up and make obstacles, and then if you can also click to determine where it wants to go, and then those purple blocks represent where the robot can see. So anything within those purple blocks is visible obstacles, and it would try to drive to the goal, and when it sees obstacles, it would drive around them. That's a very simple simulation I made. There's another video which I actually did it like I did part of it where be repel from obstacles, but it would not try to align to the goal. There was no goal at this time. Um, I can show you the videos after, I guess. The next one, there's that final video where I do this with a goal, and I had it go around an obstacle to its goal. Okay, you can skip to the slide that actually isn't a video. And then here's a visualization of dynamic window approach. I want to use this one instead because it's better with a ground robot. Because it looks at a bunch of different trajectories and finds the most optimal one based off of how much clearance it has from the obstacle and how far the angle is from the original uh goal vector. And next slide. And then there's the control system is very simple. So we want to use a PID controller to align our robot to look at the goal. So in this case, we use arctangent basically to get our target angle, and then we subtract that from our current angle to get our angle error, and then using a PID controller, we can rotate our robot to that target angle. But to actually move to it, we can't just use a PID controller with distance because since it's using tank drive, that means it can't just drive in the direction of the target without looking at it first. So what I've noticed is the logic here is if the angle difference is greater, that means you should be turning more, not driving more. But if the angle difference is smaller, like you're looking generally at it, you should be driving more than turning. So I found that as a cosine relationship and use that in my PID controller. All right, next slide. All right, so here's the arm logic. We don't have an arm yet, but I have gotten some time to play with an arm. That's just a video where I use YOLO to detect cups and have Joseph's arm pick up the cup. It was just proof of concept, so we could theoretically do that with fruit or weeds too. Identify the weeds using YOLO, and then move the arm or have the robot align to the weed or fruit, and then have the arm go extend and pick it up. And it knows how far to go by using a camera on the arm that has like depth of vision. All right, next slide. And then finally, this is the last slide here. This is just what we've had to work on so far. Simple commands that you can actually control the robot. We have that. Wireless control, we have that. Perception, it works. Now, the other stuff though is still a work in progress. Like localization, we don't have the GPS and dead reckoning sensor fusion yet because we don't have the way to communicate with the RTK GPS because we don't have the radio yet. And then for mapping, I just need more time to work on that. And then pathing, well, it requires a lot of things. It requires good localization and good mapping to actually make good pathing. So, and then control, we have it. It works pretty well. And then finally, the fruit and weed detection. Well, we don't have that yet because we need an arm to actually be able to do that. So that's just going to require more time and an assembled arm. So, does anybody have any questions? Okay, if you're done, should I stop sharing?
Yeah, very good job, Peter and John.
Thank you.
I have some comments, but anybody else would like to say anything before me? Feel free to. Um, so this is a lot of work. Yeah, and very good presentation, first of all.
Thank you.
I really enjoyed. Um, yeah, like this doesn't feel real that you guys have done this much of work in 6 weeks. Let's say 6 to 7 weeks. Very good job.
Thank you.
Quite impressive. Mm, let me see, maybe I'll start. Okay. So the perception, simple commands. Oh, yeah. Maybe you can show me later the graphic user interface that you developed. So is it completely in Python?
The interface is actually it's all web-based, so it's in JavaScript, HTML, CSS.
The back?
The backend is Python.
Because I have seen your the graphic user interface that you developed for Joseph's arm.
Mm.
Um,
That one is in Python.
that was in Python.
Yes.
So I was wondering if it was only a local application.
That one was, yeah.
So did you enjoy coding everything in JavaScript and Python?
Yeah, it just uses a lot of languages. It uses well Python for the backend. For Arduino, it uses C and C++, and then for the actual the front end, it has JavaScript, HTML, and CSS. If that counts.
Uh, did you compare your code anytime with Claude?
It's when it didn't work usually. Yeah. Yeah, if it doesn't work, it's like, why isn't it working? And then that's when I would ask.
Okay. So then your application is not working, you're compared to with Claude.
Mm.
I should show. Okay. That's good. So could you explain the controls for what are the like I saw the PID control is part of control.
Yes.
Anything else you use as a part of control? Like do you control with joystick?
Oh yeah, yeah. So that control system I showed was a for autonomous control where we have like our target position and our current position. But for when we first made this, we had very simple controls where you just tell a joystick what direction, how fast to drive and what direction to drive in, and then the wheels would move based accordingly. Where turning is opposite direction and then driving forward is like same direction. So that was one of the first things we did. We used to have a controller too, so but now the joystick is actually on the website, so you can use your phone or a mouse to control it.
Very interesting. Yes. So, so your drivetrain base, maybe Sean can also just in here. How do you compare your drivetrains? Because I'm hearing more like maybe you both are thinking about track based right?
Yeah, we're actually currently working on a special type of drivetrain we talked about earlier in the presentation. It's
Can-
six-wheel
Can you
drive.
bring up like the first slide? Or I guess the second slide, actually.
Yeah.
Yeah, there's an image. Let's bring it up if possible.
So basically the way it works, it's six-wheel drive. The back two wheels are connected to each other. It's like a
One
two
slide
sets
down.
of three.
Yeah, there you go.
Um, so the back assembly can pivot on its own. So the front legs can lift up. And basically each side of the module is connected at the center of the robot via like a differential gearbox. So that when one track of the wheel assembly raises, the other one lowers, which keeps the center of the robot level to the ground, regardless of like what kind of obstacles it's going over.
Okay. Yeah, this is cool. You guys showed me this earlier. So I'm not more. So you don't have to put any bells on the top of this system. When I heard track,
Yeah, no, there's no.
would be like the tank wheel tracks.
Yeah,
Yeah,
that was my
no.
original idea, but he said rover, like a
Yeah,
Martian
this
rover
this
idea
is
would
the
be
type of
better.
drivetrain that that NASA rovers use. So
Yeah, better for all terrain systems environments.
yeah, because the main problem with tank treads is that when you go over really uneven obstacles, the robot can often tip because the tracks are like
Yeah, the original idea
stacked
was
next to each other.
the idea was we wanted a drive system that has like less wheel slippage, because like wheel encoders are one of the ways we measure. I mean, in an outdoor environment, there always will be wheel slippage, but this kind of will sort of like mold to the environment, so it won't slip as much. So
Okay. So, so with this mechanism, I see that there is a chance that the robot can actually uh, move in the vertical direction as well. Maybe when it has to go over the bumps,
Yes,
to be calculating the pitch or the roll from the IMU.
it could, yeah, the IMU does for that information.
Yeah, so would that be useful
Um,
sometimes because uh, the robots I was showing yesterday, we had a ramp where we were going down, so we had to control the speeds when it was going down or up. So we use that pitch and to go if necessary.
Yeah.
Or how that the pitch. Useful.
that's true. It really comes down to if we need to. What I'll do for now is assume a perfect world, don't use it until it becomes something where we need to. But we have the resources to do it. So
It's only for discussion.
hmm.
Yeah, I'm passing time by asking some questions.
Ideally, the idea though is even if it does something goes terribly wrong and the robot completely loses track of where it is, really quickly it should be able to recalculate its position using GPS anyways. So with the constant GPS feedback, um, then even if it does go up a ramp or something or slip, it should be able to quickly recalculate where it is based on the GPS information. The odometry is mainly for in between GPS readings. So
Uh, that sounds very good. I would like to see my robotics students or the other experts comment or ask me questions. Nice haircut.
Thanks.
I almost did not recognize. Very good.
Right, so.
thank you. I'll leave the meeting now.